Hello, lovely people. How is everybody doing? It's reasonably sunny outside, at least where I am. I hope it's sunny where you are. I will get started in maybe like a minute or so. Just wait for a few more people to show up. Hey, Laura. What was I going to say? I have like half a working brain apparently, because my words just disappear when I need them. So I've, as usual, got the presentation in the description. So if you wanted to download that, and in the chat. So my lovely colleague has put it into the chat. Hello, Anand. And I can see that. So the time, I don't know why the time on the live stream was 5 to 3 instead of 3 o'clock. I think that was just like a typo kind of mistake. So apologies if you all showed up early and for no reason. Sorry about that. Do I assist with AS level? Yes. So like this, Hess's Law is an AS topic, although it's used across both year 12 and year 13. Hey, Jalaj. Hey, Namrata. Hello, Plumi. What are we doing today? We're doing Hess's Law. So this is like enthalpy cycles stuff. So we're going to be having a look at some questions for that. And I have a little bit of an announcement to make. So we're sort of, this is going to be the last YouTube class for a little while. Hey, Talia. So we're going to sort of, just because lots of people are sort of have gone back to school and college and things like that. So we're sort of, the number of views have gone down quite a bit. So we're sort of going to stop for a bit, take a break. Ollie and I are going to take a break. So Ollie's the biology guy. And then sort of we'll come back and reassess and see if there's something like that we can do on YouTube that's sort of a little bit more useful for the people who aren't in school, things like that. So just for really, just for sort of a little while, we're sort of not going to be doing any more YouTube classes for a bit. So this is the last one, but you'll have me on YouTube for a bit. So just enjoy it. Right. So we're going to sort of get started then, because I sort of talked a bit for a while. You'd like to sign up for the AS level package. What package do you sign up for? So it really depends on how much help you want. There's different packages at different price points. My colleague will drop them in the chat. There we go. So my colleague said you can email support@snapprovides. Isn't there one on Thursday? There was going to be one on Thursday, but we're sort of cancelling. We're going to finish this one as the last one. Was Ollie not here on Monday? Ollie was on holiday on Monday. So no. All right. I'm going to get started. What am I doing? I am sharing my screen with you. That is what I'm doing. Holiday. Was it COVID? It was not COVID. I can assure you that it was not COVID. Start, please. That is what I'm doing, Abdurrahman. I'm starting. Right. So as usual, the setup is that I will sort of read an exam question, maybe give you a few hints, give you a little time to answer it, and then I will and then I will give you the answers and answer any questions that you have. How am I? I am a bit frazzled today. It seems to be almost a constant state of being at the moment, but yes, I'm a little bit frazzled, but that's fine. That is life. All right, so as usual, at the end, there's going to be a coupon code for our lovely website, but lots of you have seen it before, and I didn't introduce myself to the new people. If you're new, hello, my name is Georgia, welcome, and if you are not new, welcome back. Oh, you enjoyed your mock? That is fabulous. I'm glad you enjoyed your mock. How can you get SnapRevise for free? You cannot have it for free because obviously all the staff needs to be paid. So what we do is we have some YouTube classes and we have tiered pricing on the website so that like different people with different budgets can afford some different things, but we do have to pay our staff. obviously we can't work for free because we've got to eat and stuff like that. All right, how long would this live stream be? Roughly like 45 minutes to an hour, depending on things. Anyway, let's get started. So the first question is sort of a student uses Hess's law to determine a value of the enthalpy change that occurs when anhydrous copper-2 sulfate is hydrated. This enthalpy change was labeled delta HXXP or EXP by the student in a scheme of reaction. So here we've got an enthalpy cycle. So we've got anhydrous copper-2 sulfate reacting with water, and that's our sort of the enthalpy change of EXP making hydrated copper sulfate. And then we've got sort of like an enthalpy cycle that goes through some different routes. So we can sort of have a think about that later. And the first thing we want to do is state Hess's law. So that's where we're going to start. So you guys have like 60 seconds-ish to tell me what Hess's law is. So this is one of those standard definitions that you should definitely try to learn the wording of, because the question comes up quite often, and it's just, if you can just sort of like tick all the boxes, then you're going to be in a really good position. So have a go at that. How long is it today? Roughly 45 minutes ish. Might run over a bit, but 45 minutes ish is probably a good. I agree, Aziza. You don't know the definition? That's fine. You will find out the answer. How many marks is this question? I seem to have chopped off the number of marks, but I believe this question is only 1 mark. Give you another 10 seconds. Okay, all right. So lots of you have got the correct answer for Hess's law. So Hess's law just states that the enthalpy change of reaction is independent of the route taken. And I might give a little bit more of an explanation that how accurate is your answer. The enthalpy of reaction is always constant, regardless of the route taken to get to the same products from the same reactants. That's fun. That's a good definition, Karen. You've just sort of said more than you needed to. So all you needed to say to hit your marks is that the enthalpy change of a reaction is independent of the route taken. And all that means is that the energy change or the enthalpy change to go from anhydrous copper-2 sulfate to hydrated copper-2 sulfate, to go from A to B, in this case, it doesn't matter if you like literally just react with water and do it straight away. You could sort of go through like a whole other set of reaction routes. Like you could go from anhydrous copper-2 sulfate to copper-3 sulfate and then back to copper-2 sulfate and then have water. As long as you're going from A to B, the energy change is exactly the same. So that's all could you say path instead of route? Yes, you can definitely say path instead of route. So just keep that in mind. That's what we mean. Like, it doesn't matter how the reaction progresses, what your intermediates are, going from A to B will always be the same energy change. And that's super useful. And we'll see why in part 2. How are they the same? They're not the same, Mohammed. So that's the thing. They're not the same reaction, but it's sort of, if you do physics, it's that law of thermodynamics that says that energy cannot be created or destroyed, only transferred. So no matter what happens between anhydrous 2 copper sulfate and hydrated copper-2 sulfate, no matter what happens in between there, it's sort of the same energy transfer overall. Even if the energy sort of gets given out and then taken back in and then given out again and then taken back in, overall, the energy transfer is the same to get from A to B, no matter how you get there. It's not like it's the same reaction path. The reaction path is different. It's just the energy changes overall are the same. This is AQA, right? Yes. Any other questions before I move on? I'm probably going to move forwards to part B of the question. Yes? Laura, what would you like to know? Oh no. Oh, you're ready to move on. I always ask, are you ready to move on? And do you have any questions at the same time? And then the yeses and nos mean nothing. It's my fault. I keep doing that. I will stop doing that. Cool. So the next part of the question, so we're in the same question. We're still talking about anhydrous copper 2 sulfate, blah, blah, blah. But the next part of the question says, write a mathematical expression to show how delta H exp, delta H1, and delta H2 are related to each other by Hess's law. So it's another 1 mark question. So you got about a minute. And while you do that, I'm going to finish eating my biscuit. I like your replacement delta, Benian. That's quite smart. Also, Benian, am I saying your name right? I should have asked that. Is that a reasonable pronunciation of your name? Was it sort of like more like Benien? Is it French? Okay, I will give you guys the answer. Most of you've got it right. So the answer, I'm saying it perfectly. Okay, good. I'm glad. So the answer should be, so you could rearrange this, by the way. So if you had your answer rearranged algebraically, that's fine, but you should have delta Hx, so the reaction on the top is equal to delta H1 take away delta H2. So just in case anybody is sort of, yeah, so there's like 3 answers to this question. So you could have also said delta Hx plus delta H2 is equal to delta H1. So you can essentially, just rearrange the equation however you like, as long as it's sort of still the same. You've had lots of people say benign. I can, oh, right, you bet people have said benign instead of Benien. Yeah, I can see that. Yes, so what I was gonna say before I let myself get sidetracked, as usual, was that just in case anybody's confused about why this is the case, it's because, as I was saying, with Hess's law, it doesn't matter which route you take, as long as you're going from A to B. So obviously we're trying to figure out delta Hx, and going from sort of adding on our delta H1 makes sense, right? Because the arrow's going in the same direction. So that makes sense. We're still sort of going along the path that's going to eventually get us to hydrated copper 2 sulfate. But the delta H2, the arrow is going in the wrong direction. We need to be getting to B. We need to be getting from A to B if B is the hydrated copper 2 sulfate. So because the arrow for delta H2 is in the wrong direction, that means we need to take away that value. So just in case anybody didn't know that, you can't go opposite to the arrows, right? Yeah, you totally can go opposite to the arrows. It's just that you'll have to take away that value. So think of it in terms of like, so here we've obviously got, so the arrow, this delta H2 is the reaction from going from hydrated copper 2 sulfate to copper 2 sulfate in solution. So the difference being sort of the copper sulfate with bonds with the water and the copper sulfate with not sort of the same level of bonding with the water. So what the arrow is telling us there is sort of like the energy you would need to sort of have less bonds with the water, but that's not what we want. We want to go in the other direction. So you need to take away the enthalpy value to sort of reverse it. I hope that makes sense. If it doesn't make sense, shouldn't the arrows be going up for the elements and down for combustion? So this isn't, I want you guys to try and do, Stacey, this is in response to your question. What I would like you guys to try not to do it's useful to sort of memorize the direction of the arrows, but unless you understand why that happens, it's going to be really confusing when you come across a question like this, that is neither the enthalpy of combustion nor the enthalpy of formation. And you can be asked for unfamiliar enthalpy cycles. So you need to sort of understand why the arrows are going up and down. And you can see here that this is neither enthalpy of combustion nor enthalpy of formation. So the arrows sort of are going to go in the direction it tells you. What does Hx mean? That's just the thing, the enthalpy change that they have assigned to this. Like literally it just says in the question, this enthalpy change was labeled delta H exp. They've just given it that name. Yeah, Stacey thinks it's because it's exothermic. As in why it's called exp. Experimental, good call. I like that. You had written delta 1 plus delta exp equals minus H2 equals H2. So if we rearrange that, if we take delta 1 over, we can kind of see that you can't have, so that what you said, Synthuja, won't rearrange correctly. So you could have this and then times everything by -1, but then you would need to have a minus Hx plus a delta H1 equals a delta H2. So sort of no matter how you spin it, your one is not sort of like not rearranged correctly. You can rearrange it, but it has to be rearranged correctly. But I'm going to move on, people. So I'm hoping that you understand this one. So the next part is literally still same question, but it says use a mathematical expression that you have written in part B, and the data book values for two enthalpy changes, delta H1 and delta H2, are shown to calculate the value for delta H exp. So this question is really nice and has sort of like chopped it up into nice, pretty steps for you. So all it's trying to get you to do is do the actual calculation. So I'm going to give you a minute to do that as well. Yes, exactly, Kang. Do I think there's going to be UCAS exams? I don't know what you mean by UCAS exams, Mohammed. UCAS is sort of like the place where you apply for university. It's like the platform for that. Did you mean UCAT? Did you mean UCAT rather than UCAS? Because UCAT is the medical admissions exam. Can you make the screen a bit clearer? No, I'm afraid if the screen's unclear, it's probably your internet connection or my internet connection. Okay, so lots of you have gotten the correct answer, so I'm just going to go ahead and say what it is. So we should be doing we should be doing delta H1, which is 156, minus delta H2, so that's a minus plus 12. Obviously, a minus and a plus makes a minus. So we will have 168 kilojoules per mole. And if you did not put, if you didn't put thingy, oh, come on, brain. If you didn't put your units, then you would not have gotten your marks. So please, 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 I don't know how often I need to say it to people. If you don't put your units, you could be saying like minus 168. I don't know, what random thing shall I use this time? Cans of paint, courgettes, beans. So just please put your units. Hedgehog teddy bears. Yeah, so just please put your units. All right, So any questions before I move on to the next question? So this one was supposed to kind of ease you in by having lots of different parts. So this is probably going to ramp up and get a little bit trickier as we go. So any questions? Always write your thingy. I don't know what's wrong with my brain, but I've always had a trouble. See, this is my problem. I've always had problems with like as soon as I need a word, it just disappears from my head, which is obviously not very useful for a live stream. But yes, thingy is generally the filler that I have. Sometimes it's pigeon, but that doesn't happen in class that much. So at least I haven't just been randomly inserting pigeon. Why are the units kilojoules per mole? So the units of kilojoules per mole, firstly, because that's the standard unit of enthalpy change. So in your exam, you should always have kilojoules per mole unless it sort of states otherwise. And also, if your enthalpy changes that you're doing in the calculations are in kilojoules per mole, then your answer is definitely going to be in kilojoules per mole. How will you cope 4 to 5 p.m.? I don't know, Jalaj. My brain hopefully will still be working. Am I a robot? Not that I know of. All right, moving forwards. You're the same, Anand? Yes, somebody else. Somebody else's whose brain sort of malfunctions. All right, so the standard enthalpy change for the combustion of graphite is minus 393.5 kilojoules per mole, and that of diamond is minus 395.4 kilojoules per mole. What is the standard enthalpy change for the reaction below in kilojoules per mole? So this one, we've been given some enthalpy changes of combustion. We haven't been given an enthalpy cycle. I will draw it, so you may wish to draw it as well. So have a go at figuring it out, and I will let you know what the answer is in like a minute or 2 minutes or whatever, however long it takes for there to be a decent number of answers. I really like that you guys have started to get to know each other in the chat. It's quite nice to sort of see you guys, because at the beginning you guys didn't sort of interact at all. It's nice that there is some interaction. For the last one, not the last one forever though, Kang. I'll definitely be back, just not the next week, but I'll definitely be back. Okay, so I'm going to start talking about the answer. So I can see a lot of you saying combustion goes down, and I want you guys to stop thinking of up and down. I want you to start thinking about it in terms of what's actually happening. If you combust something, if I were going to write the combustion of this graphite just up here, if I was just going to write the equation for the combustion of graphite, the equation would go the carbon for the graphite, and then I would produce carbon dioxide and water. So the arrow for combustion goes from the thing being burned, so I would need oxygen as well, the thing being burned to carbon dioxide and water. So that's the only reason that the enthalpy cycle goes down, because that's just what combustion is, burning something and making carbon dioxide and water. So if, like, I think it's really quite important to stop just trying to think of it in terms of arrows up and down, because it's very logical. You guys know that when you combust something, you create carbon dioxide and water. So of course the arrow has to go towards the carbon dioxide and water, otherwise it doesn't make any sense. So also if you're combusting diamond, which is just a waste of diamond in my opinion, but if you're combusting diamond, the arrow also has to go towards the carbon dioxide and the water. So that's sort of the first part of your enthalpy cycle that needs to sort of be there. So then the next thing we need to think about is, of course, the fact of the enthalpy cycle, we're trying to work out the enthalpy of the reaction, right? So if we're trying to figure out the enthalpy of the reaction, we're still trying to go from A to B, which means that the arrow for the combustion of the graphite is going in the right direction in terms of energy, but the arrow going to the from the diamond to the combustion of the diamond arrow is going in the wrong direction in terms of trying to work out how much the energy changes for going from graphite to diamond. So we have to take away that value. So we should be doing the value for graphite, which is minus 393.5, take away the value for the combustion of diamond. So we'll have minus 395.4. So that should give you positive 1.9 kilojoules per mole. So that's B. Where did the carbon dioxide and the water come from? So Missimi, it's combustion. So you should know from AS and from GCSE that when you burn something, when you combust something, you make carbon dioxide and water. So that's complete combustion. Why would the arrow in diamond point towards carbon dioxide and water? So these arrows here, and I wanted to change the color, but my screen's being really annoying. And I can't get to the bit that allows you to change color. But these arrows represent the enthalpy of combustion. So they have to go in the direction that the combustion reactions go in, right? So you have to have the combustion of graphite and you have to have the combustion of diamond have arrows actually representing combustion. And combustion doesn't go from carbon dioxide and water don't react together to make diamond. That's not a combustion reaction. The combustion reaction is burning diamond and oxygen and making carbon dioxide and water. So the arrows have to go downwards. But the energy change, the energy that gets released when you burn diamonds, lots of energy is given out. So if we're trying to go backwards, we need to change the sign of the value to represent energy going in. So I hope that makes sense. Does anybody have any other questions before I move forwards? Why would you burn diamonds though? I don't know, Kang. Maybe you're trying to destabilize the diamond market by burning diamonds and increasing the prices so you can make millions, possibly. I'm pretty sure that's a film plot for something I saw at some point. I don't know why you would burn diamonds. It seems very rude to me. So how would it make sense in the other way? I don't know what you mean, Anand. What do you mean, how would it make sense in the other way? You could make a sword. You could, I mean, diamond swords are, like, I know they're in a lot of video games, but they'd actually make pretty poor swords. And you guys should know this from your chemistry for what the structure of large covalent molecules are like. So a large giant covalent lattice like diamond may be very strong, but it shatters. And you do not want your sword to shatter. You don't want your sword to shatter when you're trying to use it, right? Anand, did you want to, I'm kind of waiting for you to say what you meant by, so how would it make sense the other way around? Or does it make sense now? Is this a gaming channel? No, sorry. I was talking about chemistry technically. All right, I'm going to move forward, but Anand, if you want to sort of rephrase that question and get back to me, I will come back. All right, so the next question we have is also one where I beg of you to not just automatically use the direction of arrows, to try and think about the direction of arrows that is logical, not the one you remember. Think about the logic of what you're trying to do. So the equation for the complete combustion of alcohol J is shown below. So we have alcohol J, which is some kind of alcohol with 5 carbons, and we're combusting it with 7.5 moles of oxygen, and we're making carbon dioxide and water. And then we have a table giving us some enthalpy changes of formation shown in the table. And so we've got the enthalpy of formation of the alcohol, of carbon dioxide and water. And we're trying to calculate the combustion enthalpy, the enthalpy of combustion of the alcohol J from the information. So we're calculating the enthalpy of combustion from the enthalpy of formation. So there's both in there. So please don't just be like, oh, I've heard the formula for enthalpy of formation. I know what it's going to be. Just think for a bit. Anyway, I'll give you, yes, 3 minutes. And I don't think I should make a Twitch because literally it would just be The Sims. I don't think anybody needs to watch me build excessive houses on The Sims because that's the only gaming I have time for in my life. You've forgotten the difference between formation and combustion. Okay, VK, what I would suggest you do is kind of think about what the words mean. What does formation mean, just in English in general? What does combustion mean in English in general? That might give you a hint. And then if you can't sort of figure it out from that, then I would Google it or look in your book. PewDiePie vibes. Not too sure. Not too sure about that. Are you right? I will let you guys know if you're right once I've gone through the explanation. Then I might check my answer, Tom. Feel confused. That's okay, Ash. I will explain it in maybe like 30 seconds. When am I teaching uni maths? Me? God. I could not teach maths at university level. Zytherius. I did like 1 module of maths at university. So that would not happen. Confidence is key. Confidence is key. It's okay, Talia. We'll get there. All right. Okay, I'm gonna start telling you things. So the first thing I'm gonna do is draw my rewrite the reaction over here, because obviously I need some space to draw my enthalpy cycle. Right. So here's my reaction again. And what we're trying to do is calculate the enthalpy of combustion, because that's what it says in the question. So I'm going to write my little enthalpy of combustion symbol above my arrow of the combustion. And then I know I have my enthalpy of formation values. And if we think about what formation is, so if you remember your definition of formation, it's forming a compound or a molecule from its substituent elements in their standard states. So we should have, so for example, if I were forming this C5H12O, I would be using carbon, hydrogen, and hydrogen is in H2 in its standard state, and oxygen, which oxygen is O2 in its standard state, to make my C5H12O. And I'm not going to bother to balance that equation because A, I'm lazy, and B, you don't need to for this question, and you should not waste your time doing things that you don't need to do in an exam. So this is formation. So this, remembering what formation actually is, tells you your direction of your arrows. So if formation is going from the elements to the thing, then the arrows have, of course, got to go up. they have to go upwards because we're forming these things. We're forming the alcohol, we're forming the carbon dioxide, we're forming the water. So that's what we're doing. So again, we know we're using enthalpy of formation values, but of course, because we're using Hess's law, we have to be going from A to B. We have to be going like along the reaction path that we're trying to do. So we're actually trying to go from the reactants to the products, and this time it means that we can just go ahead and add the value of formation for the CO2 and the H2O, because that sort of energy change is already in the right direction. It's the energy given out when you're making CO2 and H2O, but the energy change for this alcohol is going in the wrong direction, because we've still got the energy change given out when we're making the alcohol, but we don't want the energy given out when we're making the alcohol. We would actually want the energy change when you're breaking the alcohol down into its substituent elements, so that we can sort of follow along a different reaction path to get to our products. So we have to take away that value, change the sign. So we know what we're taking away, we know what we're adding, but then there's sort of one last thing that we haven't had to think about yet in this live stream. We have to think about the number of moles. So if we have 5 moles of CO2, then the enthalpy change needs to be times by 5. And that's because the definition of enthalpy of formation is forming 1 mole of a compound from its substituent elements. So if we've got 5 moles, we have to times the enthalpy of formation by 5. So we're going to do the enthalpy of formation of CO2 times by 5. We're going to do the enthalpy change of H2O times by 6. And then we're going to take away the enthalpy of formation of our alcohol. So it's going to be minus minus, which you guys should know makes a plus. And that should give you minus 3,320, and again, units kilojoules per mole. So I could just shove that in. And somebody did mention, okay, so we've got some other people, why is there no value for oxygen in the table? And as people have said in the chat, oxygen is already an element in its standard state, right? So it's not like you have to put in energy to change O2 to O2, it's already O2. So you don't need to do anything with the O2. Somebody else said something before. Somebody before was saying, I came out with a positive value, so that's got to be wrong. So this is also a good thing you can do when you're doing an enthalpy change question, is check your value that you come out with and just kind of ask yourself if it's reasonable. If something's a combustion reaction, if you're burning something, it has to be exothermic, right? The whole point of burning stuff is to give out heat. So if you're working out an enthalpy of combustion and you've ended up with a positive value, it's definitely wrong. You don't get why it's negative. So a negative enthalpy value means that the energy transfer is going from the system, so the reaction that's happening, to the surroundings. So it's giving out energy to the surroundings. So the reactants themselves, they lose energy, right? Because they're giving energy out. So the enthalpy change value is negative. So Ash says, so people are asking why it's minus the enthalpy change of thingy, enthalpy of formation of the alcohol. So if we remember, so I hope that you guys were sort of getting why when we've got enthalpy of formation values, the arrow has to go from the elements to the thing you're forming. So this value here, the minus 366, that is the enthalpy of formation of this thing. So that's this formula up here. They're going from carbon, hydrogen, oxygen to the alcohol. So that's the value we've been given. So I've drawn that in our little sort of diagram, our enthalpy cycle, and shown it with this arrow here, the one I've sort of just drawn crosses through. So that's sort of saying, okay, so we've been given that value, so we're going to be using that one to figure out our enthalpy of combustion. But remembering Hess's law, right? If we remember Hess's law, all that Hess's law says is that it doesn't matter how you get from this alcohol and oxygen to carbon dioxide and water, the overall energy change is the same. So as long as you're going from that to the carbon dioxide and water, the energy change is the same, which is why we're using sort of enthalpy of formation values. But the problem is enthalpy of formation is not going to get us from A to B if we use the values as given, right? Because as we've just said, the enthalpy of formation of the alcohol is going from carbon, hydrogen, and oxygen to the alcohol, and from carbon, hydrogen, and oxygen to the carbon dioxide and the water. But we need it to go this way. We need it to go from the alcohol to the carbon dioxide and water to get a value for enthalpy of combustion. So the way that we do that, the way that we fix the values of enthalpy of formation so that we can sort of follow along the path in the right direction, the one that's going to tell us the enthalpy of the combustion, is that we sort of take away any of the values that are going in the wrong direction, and we add any of the values that are going in the right direction. So I hope that makes sense. I'm hoping that makes sense. So in terms of balancing things, so I've had a few people ask if you need to balance the equation. So you only need to balance the equation in your enthalpy cycle when it's asked you specifically to draw one. So if in the question it says using an enthalpy cycle or using or draw an enthalpy cycle to help you calculate, then the enthalpy cycle itself has to be accurate. So in that case, you would need to balance it. But if you're just doing it for your own purposes, then you don't have to, essentially. So Thelini's just sort of given an equation, and the equations are useful, but sometimes they're not. So for example, this question has both enthalpy of combustion and enthalpy of formation in it. And so many times have I seen students see a question that has both enthalpy of formation and combustion mentioned and have no idea which formula to use, the enthalpy of combustion one or the enthalpy of formation one. So if you know how the enthalpy cycles work, you never have to remember the formula and you can't confuse them, which is why I don't really teach them. I teach how to figure out what they are. But yes, if they work for you, then use them. But if you think you're going to confuse them in questions like this, don't. All right, I'm going to move forwards because we've got, how many questions have we got left? Oh, this is the last question. Yes. Okay. That means my timing is reasonable. Your teacher says it's like a journey. You're going on a journey. It's kind of like a journey, right? Yeah, maybe I should say something like that. Like you're going backwards up a road or something. That's maybe a good, I'll have a think about that. Thank you, Kang. All right. So the last question is kind of going to be like the other way around of the question that we just did. So this question says, this table shows some enthalpy changes of combustion. So this time we've been given enthalpy changes of combustion values. And the enthalpy change of formation of glucose, so that's delta HF, and glucose, which is C6H12O6, cannot be determined directly. And the equation for this enthalpy change is shown below. So we've got 6 moles of carbon, 6 moles of H2, and 3 moles of oxygen, giving us our C6H12O6, and it says use the enthalpy of combustion values in the table to calculate the enthalpy change of formation. So things are a little bit topsy-turvy compared to the last question. I'm going to give you another about 3 minutes to have a go. And try to think about what combustion actually is in terms of which directions the arrow should go, please. Except for one takes the bus. Yeah, I've never thought of journey analogies. I don't think I got any journey analogies. I can't remember how enthalpy was taught to me. I remember that when I looked at it again in my degree, I realized I had not actually understood it during my A levels. So perhaps it would have been useful to have those analogies. So it's also going to be super useful for you guys to think about whether enthalpy of formation is likely to be exothermic or endothermic. And then you can sort of check your own answer. give you another 30 seconds or so, I think. It's not the last video forever. It's just the last video for a little bit, just for a while. All right, I will do the thing where I tell you things. How long? I'm not sure. We're just sort of, because obviously, like, the problem is we started this in response, so like these specific streams in response to schools closing. So that was why we were doing this particular setup with these particular streams at these particular times, right? But now lots of schools are reopening, so we're kind of reassessing, and we also don't know what's going to happen in September. We don't know what's going on with like university admissions. So like, we're having to play everything really very much by ear because of the whole, pandemic thing. So just that's why I can't like give you a date. I don't know. I don't know. But yes, I will do the question. That is what I'm doing. Cool. So again, we're looking for the enthalpy of formation. So I'm going to draw the little delta HF to remind myself of that above my arrow. And we have been given values for enthalpies of combustion. So of course, enthalpy of combustion means going from whatever we've got there. So for example, carbon reacting with oxygen until we have carbon dioxide and water. So if we're doing enthalpy of combustion, then of course the arrows have to go towards the carbon dioxide and the water, because that's the reaction that is taking place. So of course we would need oxygen in that reaction too, but again, this question did not ask me to draw an enthalpy cycle, so I'm not bothering to write the oxygen on, but technically we should have some oxygen there, and any of the extra oxygen that you might need for that bit. All right. But of course, we're not trying to make carbon dioxide and water, we're trying to make glucose. So we technically want to be going through carbon dioxide and water and back up to glucose. So the arrow going to the carbon dioxide and the water on the left is going in the right direction, but the carbon going away from the glucose to the carbon dioxide and water is not going in the right direction because we're trying to make glucose. So we have to take away that value to account for that. That's what we're going to do. We're going to add the enthalpy of combustion values for carbon and hydrogen and take away their combustion values for glucose, which means which means that I now need to think about my number of moles. So I have 6 moles of my carbon. So I'm going to do the minus 394 times 6. I have 6 moles of the hydrogen, which is going to be minus 286 times 6. And I'm going to take away my value for glucose, which is 2,801. So the value I should have gotten, so that's a minus, so it will turn into a plus. So what I should have gotten is minus 1,279 kilojoules per mole. And lots of you got that, so well done. And I'm going to miss you guys too. I will be back though. I keep saying that. It's just a break. It's a break while we sort of get a sense of what's happening with the schools. It's just a break. But I will miss you guys as well within the break. You will see me. Yes, and if you're in year 11, you've got plenty of time to be using SnapRevise. But that was the answer. I hope that you guys sort of understood everything. Does anyone have any questions before I sort of finish off? Is Maths and Physics still running on YouTube or not? So I believe, Jalad, that Maths and Physics is also going to stop at the end of this week. So that's what I think is going to happen. Don't leave us. I'm not leaving you. I keep saying this. I'm not leaving. It's like we're taking a break from a relationship, or it's like going on the summer holidays. Why don't we think about it that way? It's like the summer holidays instead of, stuff like that. I got a minus answer, but isn't formation always positive? No. So formation, remember your rule about bond making and bond breaking. So bond making always releases energy, bond breaking always takes in energy. So for enthalpy of formation, most of the time, you're sort of doing more bond making than you are bond breaking. So a lot of the time, enthalpy of formation is exothermic. There are a few exceptions, but mostly it's exothermic. Oh, you guys are very sweet. I'm sorry. We just have to sort of play everything by ear at the moment, and I really appreciate you guys coming to all of these. Yes, so I will be back for my lovely YouTube students. The little structure you have in your timetables have been ripped up. Oh my God, stop making me feel so bad. I will be back. Is combustion always exothermic? Yes, because it wouldn't work as a combustion reaction if it was endothermic. Combustion reactions are by nature, they're like chain reactions. So like you start with a little bit of energy and then they produce more and more energy and like combust more things. That's why fires are so dangerous, because they sort of give out energy, which sort of increases the amount that they can burn, if that makes sense. But yes, if you guys are worried about how you're going to plan your time, come up with a routine, or like have one thing in your day that you definitely do. So like, I don't know, like for example, as soon as I get out of the shower in the morning and put some clothes on, I play the piano for half an hour all the time. And that way I make sure I get my piano in my day before I start work. So like pick something like that and attach it to something that's already a routine, like showering or eating lunch. And then it's much easier to create a routine for yourself. So that is my tip. All right. Okay, I'm going to finish off, guys. So like, of course, you guys know all about our website because I say it every time. So have a look. That's a shame, Jasmine Infinity. You're welcome next time when we're back. Just an interest. So KP expressions, do you need brackets? Not really, no. You can use them. Chemical energy, you guys can still study. All right, I'm gonna finish off. Make sure you sort of have a look at our website and then sort of subscribe if you would like to sort of see more in terms of Snaprovise. As usual, you have a code, so go ahead and use the code if you'd like to. Your school doesn't give you homework, so this is like a substitute. You can also, so while we're sort of taking our break from YouTube, go back and watch some of our old live streams. We did live streams at the very beginning of the year and like October, so you could do that as well. But those of you who are in my classes on the website, I will see you in 6 minutes for alcohols. But I'm going to go so that I can get coffee before that class. It was lovely. It's been a pleasure, and I will be back. Just make sure you keep studying. Have a routine. Give yourself a routine, people.